Let's go ahead and I guess start the recording then, and let's go ahead and get started. So again, thank you for joining me on a Friday to go over for your Math 1324, and then it can also help you for your NCBM 0324. So for today's session, we're going to be reviewing for your third exam. Okay, so the topics for today's review are from Chapter 6. We're going to be looking at 6.1, 6.2. 3, 4, 5, and 6. So again, because I'm sharing my screen, I don't see if you're raising your hand or you're putting anything in the chat. So please feel free to unmute your mic and stop me at any point of my presentation if you have any questions on the material, and we'll go ahead and pause. Okay, so then let's get to it. Let's start with again 6.1. 6.1, its title is Solutions of Systems of Linear Equations. So when they're asking us to solve for a system of equations, what they want us to find out is where these two lines, again, linear equations are when we're looking at lines, where the two lines intersect. And that point of intersection is a point that is shared by both lines. In this case, if we are dealing with two lines, as these examples here. So in our first example here for number one, they're giving us two lines and they want us to determine if the ordered pair of points here is a solution for the system. And for it to be a solution of the system, this point here, negative 1, 3, says that it has to give me a true statement for both of these equations. And that will be the solution for the system. So let's go ahead and do this. So what I'm going to do is I'm going to plug in negative 1 for x and 3 for y. And I'm going to start with doing it for equation 1. So these are my two equations, equations 1 and 2. Let's start with equation 1. So I have equation 1, which is 2x plus y equals 1. So everywhere I see x, I'm going to plug in again the negative 1. And for y, I'm going to plug in 3. So let's go ahead and do this. My x is negative 1, my y is 3, and let's go ahead and simplify. So 2 times a negative 1 is a negative 2. Then the 3 is by itself. So we have negative 2 plus 3. This is going to give me 1. And if you see here, when I add these two, it gives me a true statement. 1 is equal to 1. So far so good. So we know that that point is a solution of that first equation. But for it to be a solution of the system, it also has to give me a true statement for equation 2. So let's go ahead and do it. This is equation 2, which is negative 3x plus 2y equals 9. And again, just like before, I'm going to replace the x with a negative 1, the y with a 3. And let's go ahead and simplify. A negative 3 times a negative 1 gives me a positive 3. A 2 times 3 will give me a 6. And when I add 3 plus 6, I get 9. So hence, it also gives me a true statement. So what this means is this point, negative 1, 3, is a solution of the system. Okay? So, and that was because it gave me a true statement for both equations. All right, let's do example number 2. Now we have the point 2, negative 5. So let's do this process again. I have my first equation and second equation. Let's start with the first equation. So for the first equation, I'm going to plug in 2 for x, and I'm going to plug in negative 5 for the y. Yes? So we got to be careful. We are dealing with the decimals, right? So we have 0.5 times 2 gives me 1, and 8 times a negative gives me a negative number, and 8 times the 0.5 is going to be 4. So we have 1 minus 4, and when I subtract 1 minus 4, I get negative 3. Great, I have a true statement. So this point, 2, negative 0.5, is a solution for equation 1. But for it to be a solution of the system, it has to, line 2 or equation 2 has to also give me a true statement. So let's go ahead and do it. Again, my x is going to be 2. My y is going to be a negative 0.5. Okay, and this 2 stays the same, but a positive 5 times a negative 0.5 gives me a negative 2.5. And when I subtract those two numbers, 2 minus 2.5, I get a negative 0.5 is equal to a negative 0.5. So then again, since this point gives me a true statement for both equations, then the point is, oh, excuse me, I'm reading this wrong. So I didn't get a 0.5. I got a negative. I had a whole number, missed a decimal, right? So then this is not a solution. Since it's not a solution for the second equation, um, this point is not a solution of the system because
I
both equations.
apologize, Mr. Carrizales. Can you
Yes, ma'am.
click on the hide button on your
On the.
screen?
Oh,
Just because it's
yes.
blocking part of your answers.
Oh, thank you.
Oh,
Yes, is
thank
that
you,
better,
Mr.
right?
Carrizales.
Yes. Okay, there we go. Thank you for pointing that out. So now we can see the whole words. So I have it in writing there. Since the order pair 2 and negative -0.5 does not make both equations true, then the order pair is not a solution of the system. Okay. All right. So let's go ahead. So this one was a yes. This one is a no, not a solution. All right. So another way that we can solve systems of equation is by graphing. So let's practice that. Let's go ahead and practice solving systems of equations by graphing. So I have these two equations. Y is equal to 3x minus 6. And we have, that's our first equation. Our second equation is negative 5x minus 2y equals to negative 10. So again, because we're graphing, let's review a little bit of our slopes and which will help us graph. So on equation 1, it shows me that my slope is 3, but I want to write it as a definition of what slope is. Slope is rise over run, right? So to convert that into a fraction, I have 3 over 1, right? So it means I'm going to rise 3, run 1. That's my slope. Now the b part of this equation, because it gave me the equation in slope-intercept form, this negative 6 represents my y-intercept, where the line is crossing the y-axis. So again, as an ordered pair, my y-intercept is 0, negative 6. So if I were to graph this first equation, again, I start with my y-intercept. I would place where my point is crossing the y-axis, and it would be down here at this negative 6. Okay, my slope is 3 over 1, so I'm going to rise 3, run 1. So from the negative 6, I'm going to go up 3, negative 5, negative 4, negative 3. Those are my three values. Run 1, it's a positive value 1. So here's my other point. To draw my line, I just connect those 2 points. So there's my first equation. Let's do the same thing for equation 2, but equation 2, they gave it to us in general form. So what I would do first is let's go ahead and convert this into slope-intercept form so the way we can graph the same way we did the first equation. All right, so let's put it into this equation. Y is equal to mx plus b, which is my slope-intercept form, and all I have to do is solve for y. So the first thing I do is I'm going to add negative 5x on both sides. And when I do that, I get a negative 2y is equal to 5x minus 10. Then the last thing I need to do is I'm going to divide by a negative 2 on both sides. Okay, so when I do this, I get y is equal to a negative 5 halves x plus 5. So now I have everything to graph this equation. I know that my slope is a negative 5 over 2, and my y-intercept is 0, 5. So again, I plot first, I start with my y-intercept. My point of intersection here is at the 5, but this one has a negative slope. So that means I'm going to go down 5 and run 2. So when I go down 5, I'm at the 0 here, run 2, I'm at this point. Then I connect the two dots, and this is my line. So my first equation was here in purple. My second equation is here in red. So the solution for this system is where these two lines intersect, where they share the same point. And hopefully we can see that the point where these two intersect is our solution, and our solution is here at 2, 0. Okay, so this is a way that we can solve system by graphing. But you see that graphing could possibly be very difficult, because what if the point of intersection was in the middle of 2 points and it wasn't the value exact? So it would be very hard to discover this point. So we have a method to help us solve um, any linear system. So this is um, another method, and we'll have another method to also solve. So the second method that we're going to use to solve systems of equations is by this substitution method. And just like the name sounds, the way to solve linear systems using substitution is by um, solving for a variable in one of the equations and substituting that variable into the other equation. So on this example is pretty nice because they already did that work for us. One of those equations, they solve for the y variable, which is in slope-intercept form. Y is equal to 3x minus 6. So in order for me to use the substitution method, again, I have these two equations, 1 and 2. So what I'm going to do, since equation 1 is already solved for one of the variables, I'm going to substitute it into the second equation, okay? So this is my second equation. My second equation is minus 5x minus 2y equals negative 10. And everywhere I see y, I'm going to put that equation 1, when y is equal to from equation 1. So y is this value, the 3x minus 6. So let's go ahead and do that substitution. I'm going to plug in 3x minus 6 to y, and then I'm going to simplify. But first, I need to distribute that negative 2. So when I distribute the negative 2 times 3x gives me a negative 6x. A negative 2 times a negative 6 gives me a positive 12. Let's go ahead and combine my like terms. I have a minus 5x plus a negative 6x. So this gives me a negative 11x. Now I'm going to move the 12 to the other side by subtracting 12 on both sides. This is going to give me a negative 11x is equal to a negative 22. And then my last step is to divide by a negative 11 on both sides. And when I do that, I get x equals to 2. So I have, and this value for x is true for both equation 1 and equation 2. So to get the value for y, all I have to do now is substitute this x to either of the two equations. It doesn't matter which one you plug it into, it's going to be the same. Now, again, what we tell our students all the time is use the easiest equation to solve for it. It doesn't matter. So for instance, in my case, I think equation 1 is the easiest one because that one is already telling me what the y value is. So that's where I'm going to plug in this value to my equation 1. All right, so everywhere I see x, I'm going to plug in 2. So x is 2 here, so we have 3 times 2 is 6, and 6 minus 6 is going to give me y equals 0. So the solution for this system is going to be 2, 0. Yes? So again, this method is called the substitution method. All right, now let's try the final method that way we can use to solve systems of equations, and this one's called the elimination method. And I like to tell my students, again, just the way the name sounds for this method, an elimination method. To do the elimination method, you have to eliminate one of the variables. And once you've done that, then you can solve for the other and you'll have your solution. So again, to use the elimination method on this one, what we want to do first is we have these two equations and we want to eliminate one of the variables. It doesn't matter which one it is. You can eliminate the x or the y. But in order for us to do that, both equations have to be in the same form. So you see the first equation is in an awkward form. It's just x equals minus 2y plus 19. The other one is in general form, which is the form that we want. We want it in the form 4x minus 3y is equal to negative 1. So what I'm going to do is I'm going to take equation 1 and I'm going to put it into proper form, meaning the ax plus by equals c. So to do that, all I have to do is move that minus 2y to the left. So I'm going to add 2y on both sides. It's going to give me x plus 2y is equal to 19. And now it's in general form. So now that I have two equations in the same format, now I can eliminate one of the variables. Now, what I also tell my students is also pick the variable that's going to be easy to eliminate. Now, in this case, both of them are easy to eliminate, but what I like to do is I always like to pick the one where they're different signs. But here, let's just go ahead and practice by eliminating our x's, right? We always want to deal with the x first. So if I want to eliminate my x's, okay, what I would need to do for these two to eliminate the x with a 4x, this equation 1 would need to be a negative 4x. And by adding a negative 4x with a 4x, that eliminates my x value. I get 0, right? So what I'm going to do that is I need to have that x to be a negative 4. So I'm going to multiply by negative 4, but please be careful. We just not gonna multiply negative 4 to the x. When we multiply this negative 4, we have to multiply it to the whole equation. That way we don't unbalance our equation. So when I multiply negative 4 to all of equation 1, we get negative 4x minus 8y is equal to negative 76. Okay, so now that I have that value on this equation, I am going to add it to equation 2. And when I do this, you'll see that I eliminated my x value. So negative 4x plus 4x is 0. Negative 8y minus 3y is negative 11y. To solve for y, I'm just going to divide both sides by negative 11. And when I do this, I get a 7. So then what I can do is I can plug in that 7 to either the two equations, either to equation 1 or equation 2. But let's make it easy for ourselves. Let's plug it into equation 1 that already has it solved for x, yes? So I'm going to use equation 1. And everywhere I see y, I'm going to plug in this 7. So we have negative 2 times a positive 7 gives me a negative 14 plus 19. And negative 14 plus 19 is going to give me a positive 5. So the solution for this system is 5, 7. The x value is 5, the y value is 7. Yes? All right. So let's go ahead and try a different one. And we're going to practice again with the elimination method. Let's solve this system. 3x minus 2y equals 4. 6x minus 4y equals 8. So on this one, they are both in proper terms. So again, it doesn't matter who we eliminate from either of these two equations, from equation 1 or equation 2. So what I want to do is let's go ahead and let's do this again. Let's eliminate the x value. Okay, so to eliminate the x value, I'm going to multiply a negative 2. And you'll see that if I multiply negative 2 times 3, that's going to give me the negative 6, which will eliminate my x value. So let's go ahead and do that first. Negative 2 times 3 is at negative 6. Negative 2 times a negative 2y is a positive 4y. And the negative 2 times 4 is a negative 8. I am going to add it to equation 2. And when I do this, I get negative 6x plus 6x is 0. 4y minus 4y is 0. Negative 8 plus 8 is 0. Now, this is a true statement, right? 0 is equal to 0. But what does this mean when we have this answer that we have 0 is equal to 0? Well, what this means is that these two lines are basically the same line. Or one way you can think about it is that it's one line on top of another line. So what does this mean as our solution? This means that our solution for the system is an infinite number of solutions or answers. Because again, you can think of it as the same line or just two lines on top of each other. And since lines go forever to the left and go forever to the right, we have infinite number of solutions. Now, one way you can see this is if you would both put these into slope-intercept form, you would see that you would be dealing with the same line that has the same slope and the same y-intercept. Okay, so let's try this next example, number 7. Solve the system by elimination. Again, we're going to do the same thing. We have equations 1 and 2. We want to go ahead and get rid of our x value. So on this example, I'm going to multiply a negative 3 to equation 1. So when I do this, a negative 3 times 2 is a negative 6x. A negative 3 times 5 is a negative 15y. A negative 3 times 8 is a negative 24. I'm going to add that to equation 2. And when I do this, I get a negative 6x plus 6x is 0. Negative 15y plus 15y is 0. Negative 24 plus 18 is negative 6. This answer is not a true statement. 0 is not equal to negative 6. So whenever you get something like this that is not a true statement from the get-go, is saying that this two lines have no solution. Um, so what does this mean that it has no solution? This means that we're talking about two lines that are parallel to each other. Um, when we have a no solution, if I were to convert these two lines into its slope-intercept form, you're going to see that they have the same slope but different y-intercepts. That means that they're parallel and they'll never cross. Since they never cross, they'll never share anything, hence the no solution. Okay. All right, so now let's look at a business problem that deals with linear systems. So we have this problem says a 200-seat theater charges $8 for adults and $5 for children. If all seats were filled and the total ticket incomes was $1,435, the question to us is saying how many adults and how many children tickets were sold or in the audience, right? So let's to solve this, let's use a little bit of what we know of our basic business concepts. Okay, so we need to find two equations because we have two unknowns, and we can do this. We have enough information to come up with the two equations. All right, so the first is to use what we know about revenue. Okay, so the seats deal with with the purchase of the price of the ticket, depending on whether it's adult or children, will give us our two variables. And you can also think about two equations, meaning we can find an equation that deals with the number of seats, and we can deal with an equation that deals with just the money itself, right? So let's do the seats. So we can say that the adult seats are the x value, the children's seats are the y value, and we know that the theater holds 200 seats, right? So in order for us to come up with the equation, we can say that the x plus y should equal the 200 seats. Now, the money one, we can say if x is the adults, the price of the adults is $8. So that means as a equation that is 8 times x. Again, the revenue. To get revenue, it's price times quantity. Now for the children, if the children is $5 and we're using the variable y, so 5 times y is the price revenue quantity for the children, and we know that the total income that the theater acquired was 1,435. So in my second equation, the total income is adding these two variables together that equal this. So how do I represent that as an equation? It would be 8x plus 5y is equal to the 1,435. So now I have two equations. These are my two equations. So again, this was equation number one. This is equation number two. And we can use the concepts that we just went over. So let's go ahead and use the elimination method again. Let's get rid of our x. So what I'm going to do is I'm going to multiply negative 8 to equation 1. It's going to give me this. Negative 8x minus 8y is equal to a negative 1600. I'm going to add this to equation 2. By adding these two equations, we see that we got eliminated our x variable and leave us just with the y. Again, negative 3y is equal to a negative 165. To solve for y, I'm going to divide both sides by a negative 3. And when I do that, I get y equals 55. So I got one of the number of tickets sold. It was 55 children's tickets sold. So to get the x number of tickets sold, I'm going to plug it in to either of my two equations. It doesn't matter which one, but let's be nice to ourselves. Let's pick the easiest equation. I think the easiest equation is that first equation. Okay, so I'm going to use the first equation, x plus y, to get my x value. So again, y is 55. So let's replace it. So to solve for x, all I have to do is subtract 55 on both sides. And when I do that, I get x is equal to 145. And now I've solved this word problem. So the number of adult tickets sold were 145, and the number of children tickets sold were 55. And I did it solving a system of equations. Okay, so this is my solution. All right. 6.2 deals with larger system of linear equations. What this means is now we're not just solving for 2 lines, now we're solving for 3 lines, right? So the best way to do this is what we want to apply is something called backward substitution. And what we want to do is we're going to take first 2 equations, get rid of one of the variable, get 2 different order pairs of equations, and get rid of one of the variables. Then we're going to be left with 2 equations that only have 2 unknowns, and then we can eliminate one of those variables again, just like we have been doing before. It's going to leave us with only one answer. And then what we can do is we can just replace those variables going backwards. Again, the best way to see this is with an example. So what I'm going to do is I'm going to take equations 1 and 2, and I'm going to get rid of one of the variables. Okay, so what I'm going to get rid of is I'm going to get rid of my x variable. I'm going to try to keep this all uniform. Now, it doesn't matter who you get rid of. Again, I'm just trying to have everything um, repetitive so you can see and practice. All right, so I'm going to get rid of the x from equations 1 and 2. So I'm going to multiply the first equation by -2 and get this negative 2x plus 6y minus 4z equals 0. I'm going to add it to second equation. So when I do this, I eliminate my x value. I get 4y minus 3z equals 3. Now what I need to do is I need to get another different set of equations. So this is my equation 2. So now I'm going to use equations 1 and 3. This is a different pair. So my equation 1 is this, and my equation 3. And I'm going to do the same thing. I want to get rid of my x again. So what I'm going to do is I'm going to multiply a -3 to equation 1. So when I do this, I get a -3x plus 9y minus 6z equals 0. I'm going to add it to that equation 3. And when I do that, you see that my x got eliminated. I get 10y minus 7z equals 7. So this is a new equation. So now you see these 2 new equations. Now I only have 2 variables, y and z. So what I'm going to do is, these are my new 2 equations. Now I'm going to get rid of the y. Yes? So to get rid of the y, I'm going to multiply the first equation by a -10. And when I do that, and I need to multiply equation 2 with a +4. So when I do this, I get a -40y plus 30z equals -30. My second equation, when I multiply a +4, I get a 40y minus 28z equals 28. And this is going to allow me to get rid of my y's, because when I add these two together, a -40 with a +40 got eliminated, and I'm left with 2z equals -2. So to solve for z, all I have to do is divide both sides by 2, and I have this value, -1. Here's where the backward substitution comes into play. Okay, I have already one solution. So what I'm going to do is I'm going to replace this value that I know to one of my 2 new equations, either equation 2 or equation 3. Doesn't matter which one, but I'm going to replace it to get my other variable. Okay, so here I have this. I'm gonna use, if you see here, I'm gonna use the equation 2, my new equation 2. The 4x minus 3z is equal to 3. I'm gonna work backwards. Okay, so this is where the backward substitution is. So I start, the 4y minus 3z equals 3. I know what z is, so I'm gonna replace that z with that -1. And when I replace it, I get a solution for my y. Okay, so my y value here is 0. Again, -3 times a -1 is a +3. Subtract 3 on both sides. 3 minus 3 is 0. Divide by 4 on both sides. I get y equals 0. So now I have 2 variables, and I'm going to plug it into that first equation, that x minus 3y plus 2z equals 0. So I have those 2 equations. So my y is 0, my z is -1, When I simplify my work, add 2 on sides, x is equal to 2. Hence, I have my solution. My solutions are 2, 0, and -1. Okay, so this is the way to do it when we have a larger system of equations. We want to start eliminating variables until we get to only one solution, and then we work ourselves backwards. It's called back substitution. Okay. All right. So another method to solve is also called that is used is called the Gauss-Jordan elimination method when we're dealing with larger system of equations. So one way to do this is to convert our system to what's called an augmented matrix. We want to use matrices to solve these systems. So first, let me represent our linear system. So let's say that we have a linear system. We want to convert it into its augmented matrix form, and then we're going to solve by this Gauss-Jordan elimination method. Now, you have this word here, RREF. Um, this is the term that is used like on calculators to use the Gauss-Jordan elimination method. Okay, so let's do this process. Okay, um, first I have this linear system. So an augmented matrix, matrix, just to review a little bit, matrices is a way that our calculators can solve linear systems. Um, and since matrices have a placement value, each matrix, the position of each value in the matrix has a position. So we don't have to worry about the variables anymore. We just have to put in the coefficients because the matrix is going to have our placement value already for us. So how do I represent this linear system as an augmented matrix form? Is just by putting in the coefficients here. The first one, the coefficient for the x is a 1, so I have a 1 in that first place value. The coefficient on the second place for my coefficient for the y is a -3, so that's why I have a -3, 2, and then my solution is 0. Similarly to that second equation, I'm just grabbing the coefficients. It's 2, -2, 1, 3. And we have 3, 1, -1, 7 for our last equation. Okay, the way we represent an augmented matrix form, the way we represent the equal sign in our augmented matrix is by this line, and we call it a pipe, or it's just a line. This line again represents our equal. So to solve this, what we want to reduce our augmented matrix is into this form. Okay, this is the identity matrix, or the identity um, notation for this matrix 1 0 0 0 1 0 0 0 1. So what I tell my students, this representation is, think about solving for the intercepts. If you want to solve for the x-intercept, you set all of the other variables equal to 0. And when you do that, you get the solution for the first value with the x. If I want to solve for the y-intercept, well, I set all of the other variables equal to 0, and I have my y value. And similarly also for your z. If I want to find the intercept for the z, I set all of the other values equal to 0. So when I have it in this format, 1 0 0 0 1 0 0 0 1, the solution that by getting these values into this format gives me the solution of the system. The solution is going to be 2 0 -1. Now let's go ahead and practice doing this. Okay, let's get this to look like this. So how, right? Um, Let me show you the steps on how we got to that process. Okay, so first we're gonna write our linear system as an augmented matrix form, which is here. All right, so now we want to do row reductions, and that's where that name comes from. The RREF came from this reduced row echelon form. Okay, and again, it's the name that the name that your calculator can give you to solve for this. All right. So first, this is what I want, and we color coded it in order for us to help you on how we're getting these values. This is the solution already when it's in reduced row echelon form, but let's get it into that. So let's practice the syntax. each row in our matrix, we're going to designate it as row 1. R1 means we're dealing with this row, 1, -3, 2, 0. Okay? Similarly, a row 2 is 2, -2, 1, 3. And our row 3, we're going to call it 3, 1, -1, 7. Okay? All right, so step 1. We want to follow these steps. You want to follow these orders, just like anything, like just how you read, graphs. We do things from left to right. So we want to get these zeros in order. We're going to start with the first column, then we go to the second column, then the third one, until we have our solution. Okay, so the first thing, we have a 2 here that I wanted to make into a 0. And to do that, what I need to do is, well, I'll show you right now. And then also on row 3, the 1, 3 that's in blue, I want that to be a 0. Okay, so that's going to give me new lines. How do I do this? So this is the syntax. So to get a 0 there, what I'm going to do is I'm going to multiply a -2 to row 1, and I'm going to add it to row 2. This process to get into reduced row echelon form is just the elimination method that we were practicing earlier, but we're just doing it without variables. Okay, so when we do this, again, to get the 0 on the third line, I'm going to multiply -3 to row 1, and I'm going to add it to row 3. Okay, so this is my scratch work to show you what we're doing. So when I multiply -2 to row 1, I get this value. And if I'm adding it to row 2, okay, row 2 is just 2, -2, 1, 3. When I add these two together, look what happened. I got rid of that x value. So my new row 2 is 0, 4, -3, 3. Let me show you my scratch work for that line 3. Okay, I want to multiply -3 to row 1. When I do that, I get -3, 9, -6, 0. I'm going to add it to row 3. So when I add it to row 3 is 3, 1, -7, 1. When I add these two together, my x got eliminated. I got a 0 now. So that's 0, 10, -7, 7. All right, so we are done with that first column. So we go to our second step, okay? Remember, our objective is to have this. All right, so my second step is I want to get a -3 here for my row 1, and I want to get a 0 where my 10 is. And we color coded them for the ones in green, right? So another rule of thumb, if you notice with my first step, the one that was not getting changed, that's the one I used in order to get new equations on the other. So if you notice here, I did the same thing on this one. My middle row, my row 2, I'm not changing anything on that one. I'm just getting a 0 for the first one and a 0 for the third line. So I'm going to use that middle one, my row 2, to do those transformations. Okay, so to get my new row 1, I'm going to multiply a 3 to row 2 and add it to a row 1. But in order to eliminate that 3, I need to multiply my row 1 by 4. And you'll see what happens. So let's go ahead and do these. So let me show you my scratch work. I'm going to multiply a 3 to row 2. So when I do this, 3 times 0 is 0, 3 times 4 is 12, 3 times -3 is -9, 3 times 3 is 9. I'm going to add that to the product of 4 times row 1. So when I multiply 4 times row 1, I get 4 minus 12, 8, 0. And when I add these two together, we eliminated our y value, or that second value, right? So that's what my first row is, 4, 0, -1, 9. Now let me pause here and let me point something out, okay? Remember our objective, we want to have a 1, 0, 0. And we had a 1 there already in the beginning, but now that we got eliminated our second step, we lost that 1. That's going to happen. Do not worry, okay? Right now, what we gotta focus on is just on the zeros. If something that was a zero and became a number, that's when you worry. But if we had a one and it became another number, do not worry. Okay, we'll take care of that at the end. Right now, we're just concentrating on getting the zeros. Okay, now let's go ahead and get our new third line. Okay, so for our new third line, I'm going to multiply -10 to row 2, and then I'm going to multiply a 4 to row 3. And when I do this and I add these two numbers to these two rows together, I have 0, 0, 2, -2. So that's my new row 3. Okay. Um, so we can simplify already here, okay, if you want to. And you only want to do this if this is possible, okay? And to simplify this, if you see here, both of the remaining values that I have are a multiple of 2. So that means that I can divide that whole line because I always want to balance my equation. Remember, the last one is an equal sign. Um, I want to um, balance equation. So I can divide by 2. So if I divide by 2, 0 divided by 2 is 0. 0 divided by 2 is 0. 2 divided by 2 is 1. And -2 divided by 2 is a -1. So this step is not necessary, but it makes our math a little bit easier. So now my third line is 0, 0, 1, -1. Okay, so we're almost there. Now we're going to the third column. Okay, we want a 0 um, where the reds are, right? So here, I want a negative 0 where the -1 is, and I want a 0 where the -3 is. Okay, again, which line is not getting altered or I'm not doing anything to? That's my row 3. So I'm going to use that to get a new row 1 and new row 2. So to get a new row 1, I just have to add row 3 with row 1, and it's going to get what I want. To get the new row 2, I need to multiply a 3 to row 3 and add it just to row 2. So let's go ahead and do the scratch work. Let's do first the first one. Row 3 is just that, not doing anything to it. Row 1, I'm not doing anything to it. I'm just adding these two rows together. So when I add these two rows together, I get these value 4008. Again, I'm going to simplify, and I'm going to do this because I see that 4 and 8 are both multiples of 4, right? So I'm going to divide by 4 on the whole row. 4 divided by 4 is 1. 0 divided by 4 is 0. 0 divided by 4, 0. 8 divided by 4 is 2. So that's my row 1. Let's go ahead and get my second row. So to get my second row, I'm going to multiply 3 to row 3, and I get 0, 0, 3, -3. I'm just going to add it to row 2, which row 2 is this. When I add these two together, I get 0, 4, 0, 0. That already is already simplified, so that's what goes there, right? Oh, sorry, we can simplify it even 4. 4, we can divide it by 4, which will give us 1, right? So when we're going to do this, we have 0, 1, 0, 0. So that goes there. All right. Now we have what we wanted, right? We have a 1, 0, 0, 0, 1, 0, 0, 0, 1. So hence our solution is x equals 2, y equals 0, z equals -1. Okay. All right. So again, to um, do another problem, let's go ahead and go through the steps here. Okay, so first, the steps. I'm going to leave row 1 the same in how it is. I want a new row 2 and I want a new row 3. Again, since row 1 is not getting altered, I just go ahead and write it. So I'm showing you my work from the step 1, the product of the -2 to the row 1, adding it to the row 2. That's going to give me these values. Again, you only want to simplify if you're not going to get into fractions and if all the numbers that are there are divisible by each other. Okay, so I see that this row is divisible by 5. So I'm going to divide by 5. And when I divide by 5, I get 0, 1, -1, 2. Okay, that's my row 2. Let's do the same thing for the third row. I'm going to add row 1 with row 3. That's all I have to do. That one's already simplified, so that one just goes there. Second step, again, now it's the second column. Um, I want a new row 1 and I want a new row 3. So since row 2 is not getting altered, I'm just going to write it. That way I don't confuse myself which ones I'm altering. I know I'm getting a new row 1 and a new row 2. Okay, so this is a syntax to get a new row 2. Excuse me, new row 1. I'm going to multiply -2 to row 2, add it to row 1. To get a new row 3, I'm going to multiply -1 to row 2 and add it to row 3. So let me show you my work. Okay, so when I do this, okay, I have 1 0 1 2, and if you see on this one, um, I there was nothing to simplify because um, they're all already prime numbers, already simplified. Okay, so let's do the scratch work for our third row. When I add these two rows together, we have 0 0 1 -1. That is already simplified. Then we got there. So that's our second step. Let's do our last step, our last column, our column 3. Again, I'm going to use row 3. Since that one's not getting altered, I'm going to write it. But I want a new row 1 and I want a new row 2. Okay, so to row 1, all I have to do is multiply -1 to row 3, add it to row 1, and I have my answer. Okay, um, to get a new row 2, I'm just going to add row 3 with row 2, and that will give me the desired outcome that I want. All right, let's do the first one, our scratch work. A -1 to row 1, it's going to give me 0 0 -1 1. I'm going to add it to row 1. Row 1 is 1 0 1 2. When I do this, I have 1 0 0 3. That's my new row 1. Let's go ahead and do it again to get our row 2. Um, so to get our row 2, it's just adding row 3 with row 2. When I add these two rows together, I get 0 1 0 1. Yes? So um, I am done. I have that left side in 1 0 0 0 1 0 0 0 1. So my solution is x equals 3, y equals 1, z equals -1. Okay? All right, so let's look at an application problem that comes from 6.3. Again, very similar to the one we had done before. And again, we're talking about a concert. So tickets to a band concert cost $5 for adults, $3 for teenagers, and $2 for preteens. So now we have three variables, right? Before we just had adults and children, now we have adults, teenagers, and preteens, right? Now, there was 570 people at the concert and a total ticket receipt was 1,950. Three-fourths of as many teenagers as preteens attended. How many adults, teenagers, and preteens attended? All right, so we can do this. So we need three equations because we have three unknowns. Okay, so our equations can be the people with the people, the money with the money, just like as before. Okay, so let's set variables: x for adults, y for teenagers, z for preteens. There are 570 total people, so the first equation is x plus y plus z will give us the 570. Yes. All right, how about the money? This is like the revenue, okay? So to get revenue, adult tickets is 5, so that will be 5 times x gives me the total for the adults. Teenagers is $3, so 3 times y will give me the revenue for the teenagers, and $2 for preteens, so for the revenue for the preteens would be the 2 times z. Now, if I add all these values together, it has to give my total receipt value. So there is my second equation. My total receipt is 1950. So 5x plus 3y plus 2z has to equal to this 1950. I have two equations, but I needed a third one. I'm going to get that third one by that third line that they gave us that says that three-fourths as many teenagers as preteens attended. All right, so what does this mean? Okay, my third equation is needed, right? So is here. This is what I just read. This is where I'm going to get that third line. So if I know that teenagers are Y and preteens are Z, what they're saying is that three-fourths as many teenagers as preteens attended. That means that if I multiply three-fourths times my preteens, that gives me the total number of teenagers that attended. And there is my third equation. Um, and it's not that difficult, right? It's just how it sounds. Just um, switch it, right? So our equation here, just if we switch it, we have y equals um, 3/4 z. Yes? So I have my three equations, but just to put it into a little bit easier for us to solve, let's just put it a little bit more generic, okay? Let's put it into proper terms where all of our variables are on the left. So again, to do that, I had to multiply both sides by 4, and then I just subtracted 3z on both sides. So I have 4y minus 3z equals 0. Now I have three nice equations that I can use, okay? That was my third equation. Here we go. All right, so what I'm going to do is I'm going to do the same thing that we had done before to kind of eliminate variables so we can have it and use backward substitution or back substitution. Okay, so these are my three equations. What I'm going to do first is I'm going to get equations 1 and 2. And what I want to do is I want to get rid of the x. The reason why I want to get rid of the x is because I have a third equation that already has no x. So half of my work is already done for me. So let me get rid of my x from my first two equations. So to get rid of my x, I need to multiply that first equation by a negative 5. So when I do that, I get negative 5x minus 5y minus 5z equals to negative 2,850. I'm going to add it to equation 2. And when I do this, I have minus 2y minus 3z equals to negative 900. Now I have two equations. You see here, this is my new equation. But equation 3 has no x term. So my work was done for me. So I'm going to use these two. Minus 2y minus 3z equals 900 with my equation 3. Let's get rid of the y. Yeah, so I'm going to multiply a2 to equation 1, giving me minus 4y minus z, minus 6z equals negative 1800. I'm going to add it to equation 3, which is 4y minus 3z. And when I do this, I have minus 9z is equal to negative 1800. Solve for z by dividing both sides by a negative 9. And I have z is equal to 200. Now I just work backwards. Okay, these are my three equations. I'm going to work backwards, back substitution. So the one equation that has two variables, I'm going to plug in my z value that I know. So I have minus 2y minus 3 times 200 is going to give me a minus 600. Add 600 on both sides. I have negative 300. Divide by a negative 2 on both sides. I get y is equal to 150. Now I just have to plug it into my equation that has the three unknowns. And again, I'm going to be nice to myself. I'm going to pick that first one. That first one's easy to solve for my remaining x. So here I have y and z already. Let's plug those in. When we plug them in, 150 plus 200 is 350. Subtract 350 on both sides. X is equal to 220. Now I know the solution. 220 tickets were sold for the adults, 150 for the teenagers, and 200 for the preteen. Okay. Now, fortunately, I am out of time. Um, but really quick, I have 3 minutes. I'm just gonna run through what matrix addition is. Matrix addition is you just have to um, add um, variable with variable. So for instance, here, if I wanted to add matrix A and B, okay, the 5 corresponds to the position of the 2 of the B, right, from the A. So basically that's what matrix addition is. You're just adding the the placement value with the corresponding placement value of the other matrix. Okay, so again, I want to thank you. Let me go ahead and stop sharing my screen because I was hearing some beeping. Um, where am I here? All right, stop sharing. There we go. So again, thank you for joining me today. Hopefully this helps you on your review. I'll go ahead and pass it out to our presenters as well. Thank you so much for joining me.
Thank you, Mr. Garisales, for your wonderful presentation. We want to remind you all about our previously recorded sessions, which are available on YouTube on the Tejano Virtual Events playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our Tejano Virtual Events sessions. Please take a few minutes to fill out that survey. Before you all leave, I want to share the Tejano Virtual Events flyer for the sessions that we will have next week. At 1 p.m. today, we will have Multimedia Studio with Fernando Mares. We will be back with Happy Math Hour next week at 11 a.m. For in 1314, we will be covering the standard form of quadratics and synthetic division. And on 1324, we will cover exam 4 review. Our 1 p.m. session next week will be on volunteer opportunities and dog fostering with Elizabeth Olivas. Thank you all for coming in today. We hope you do have a lovely weekend. If you have any questions, please feel free to use the chat box or your mic. We hope to see you, everyone, again for the Happy Math Hour next week. Thank you. Goodbye.